Unit 1 Signals and Systems. Basic elements of DSP, concepts of frequency in analog and digital signals, sampling theorem, discrete time signals, systems, analysis of discrete time LTI systems, Z transform, linear and circular convolution, correlation. Topics covered in lecture 1 are basic elements of DSP, advantages, limitations and applications of DSP, classifications of signals, representation of signals, elementary signals, mathematical operations performed in signals. Basic elements of DSP. A signal can be defined as a function that conveys information generally about the state or behavior of a physical system. The digital signal processor, which is used to process the digital signals, may be a large programmable digital computer or a small microprocessor program system to perform the desired operations on the input signals. The processor is capable of processing the digital input signals and give digital signal as its output. Most of the signals are analog in nature, so the analog signals are converted into digital signals using A to D converter, and the digital signals are processed by the digital signal processor. The desired output from the processor are digital in nature. If the applications are in need of digital output, it can be used directly, or if the applications need analog output, again it is given to a D to A converter and the analog outputs are obtained. Advantages of DSP. The attraction of DSP comes from key advantages as accuracy. So accuracy is only determined by the number of bits used. Perfect reproducibility. Identical performance from unit to unit is obtained since there is no variations due to component tolerance. Greater flexibility. DSP systems can be programmed and reprogrammed to perform a variety of functions without modifying the hardware. This is perhaps one of the most important features of DSP. Superior performance. DSP can be used to perform functions not possible with analog processing. Advantages in technology. Advantages in semiconductor technology is used to achieve higher reliability, smaller size, lower cost, low power consumptions and high speed. DSP has its own limitations. However, the significance of these limitations are being continuously diminished by new technology. Speed and cost. DSP designs can be expensive, especially when larger bandwidth signals are involved. Now DSP devices are being faster and faster. Design time. DSP design can be time consuming and in some cases almost impossible. The acute shortage of suitable engineers in this area is widely recognized. Finite word length problems. In real-time situations, economic considerations are often mean that DSP algorithms are implemented using only a limited number of bits. In some DSP systems, if an insufficient number of bits is used to present variable serious degradations in system performance may result. Applications of DSP. DSP is one of the fastest growing fields in modern electronics, used in the area where the information is handled in digital form or controlled by a digital processor. Applications include the following: image processing. So image In image processing, the image compression, decompression, recognition, and the filter operations can be performed using the digital signal processor. You can control the instruments by for the spectrum analysis, position and rate control. Noise reduction is performed using processor, and the data compression is also controlled with the help of the digital signal processor. Speech and audio. So speech compression, decompression, speech recognition, speech conversion from voice to text, equalization can be performed with the help of digital signal processor. So many military applications is performed for circuit communication, radar processing, sonar processing, missile guidance, or processed with the help of digital signal processor. Telecommunication. So in telecommunication, echo cancellation, adaptive equalization, video conferencing, spread spectrum, data communication can be performed with the help of DSP. So in biomedical application, patient monitoring, scanners, ECG analysis, EEG, brain mappers, X-ray storage and enhancements are performed with the help of DSP. So the main application is a consumer applications where digital cell phones, smart cell phones, digital TV, cameras, digital answer machine, fax, modems, interactive entertainment systems are many applications of DSP. Classifications of signals. The signals are classified based on the behavior and characteristics nature of the signals here. They are random and deterministic, continuous time and discrete time signals. Random and deterministic signal. A signal is said to be deterministic if the signal is uniquely described by an explicit mathematical expression. That is, if we are able to determine what will be the output for a particular input, it is said to be deterministic. Example, x of t equal to sin t. A signal is said to be random if the signal is unpredictable with the help of a mathematical expression. For example, noise signal. Continuous time and discrete time signal. A signal is said to be continuous time signal if it is defined for every instant of time. They are also called as analog signals and denoted by x of t. So t says continuous time, which is defined for every instant of time. Example, so this is a signal where for every instant of time the signal is defined. A signal is said to be discrete time signal if it is defined for discrete instant of time. They are also called as digital signals and denoted by x of n. So the same sinusoidal signal drawn for a discrete instant of time, so the signal is said to be digital signal. So for the representation of signal. So what are all the different ways to represent the signal is the representation of signals here. There are 4 different ways of representing your signals. They are functional representation, graphical representation, tabular representation and sequence representation. So these are the 4 different ways to represent your signals. In functional representations, signals can be represented as functions. For example, x of n equal to 2. So for every time period the values has been defined. For n equal to minus 2, the value of x of n is 2. For n equal to minus 1 and 1, the value is 4. For n is 0, the value is 3. For n equal to 2, the value is minus 1. And for n equal to 3, the value is 4. So here in this functional representation, the value of n ranges from minus 2 to 3, and its corresponding values have been given. The graphical representation. So in graphical representation, the signals are represented in terms of graph, which is with time period as x-axis and then amplitude in the y-axis. So for the same functional representation example, the graphical representation can be obtained here. So here the x-axis has the time period from -2 to 3, and its corresponding amplitude is given in the y-axis as 2, 1, 3, 1, -1 and 4. Tabular representation. So in tabular representation, the values will be given in the tabular format. So time period carries one table, and then its corresponding amplitude will give you in the another table column here. So each row carries the values here. So n is given in one row and x of n value is given in another row. So for each and every column, its corresponding values has been entered. Sequence representation. So the signals are represented by sequence representation as x of n equal to 2, 1, 3, 1, -1, 4 here in the bracket, and this arrow mark tells the origin of a signal, that is when your n equal to 0, what is the amplitude. So if that arrow marks, no, after that arrow marks, it is said to be the it is continued by the time period 1, 2, 3, and before it is as -1, -2. So this is also called as two-sided signal here. So the value is presented both for the positive as well as your negative side. Elementary discrete time signals. So what are the elementary signals we are going to use for your DSP to go for the calculations or for simplifications here? So the first signal is unit impulse or sample sequence. The unit impulse sequence is defined as del of n equal to 1 for n equal to 0, and it is not equal to 0. When n is not equal to 0, the value of del of n is 0. So the graphical representation of del of n is given as, so for n equal to 0, the value is 1. For all other values, the value is going to be 0. So this is your unit impulse or samples response. Unit step sequence. So the unit step sequence is defined as u of n equal to 1 for n is greater than 0, and n is greater than or equal to 0, and 0 for n is less than 0. So the graphical representation of u of n is when n is greater than or equal to 0, the value is 1. For n is less than 0, for all other values, the value is 0. Ramp sequence. The ramp sequence is defined as r of n equal to n for n is greater than or equal to 0, and 0 for n is less than 0. The graphical representation of r of n is given as, so for n is greater than or equal to 0, this corresponding value will be your r of n. Suppose if your n is 5, then r of n is 5. If your n is 100, the r of n is 100. But when n is less than 0, the value is 0. Exponential sequence. The exponential signal is a sequence of the form x of n equal to a power n for all values of n. When the value of a is greater than 1, then the signal grows or the sequence grows exponentially. When the value of a lies in between 0 and 1, the sequence decay exponentially. And when a is less than 0, the signals take the alternating signals. So the mathematical operations that can be performed on a discrete time signals are time shifting, time reversal, time scaling, amplitude scaling, signal multiplier. signal addition. So these are all the basic mathematical operations that can be performed on a digital signals. Time shifting. Time shifting operations on a discrete time signal is represented by y of n equal to x of n minus k. That is, the signal y of n is obtained by shifting the x of n by k units of time. So the general formula is x of n minus k. If k is positive, shift right, that is delay. If k is negative, shift left, that is advance. That is, the time shifting is obtained as first the x of n signal has been plotted and the k value is obtained from the statement. After obtaining the k value, the value will be added to the starting time period of your x of n. Then it will be shifted. For example, if the x of n is 1, 2, 2, 1, 3 with the time range of 0 to 4, plot the x of n from the time range 0 to 4 with its corresponding amplitude as 1, 2, 2, 1 and 3. Then if in x of n minus 1, the k value is positive, that is 1. So after obtaining the k value 1, it is added to the origin, that is the starting value of the signal x of n. The starting value of your x of n is 0. So 0 plus 1 is 1. So in x of n minus 1, the value starts from 1. From 1 we are going to have 5 values, that is 1, 2, 3, 4, 5. So it is shifted right, that is delay. Instead of starting from 0, it is delayed by 1 unit of time as it starts from 1 in your x of n minus 1. So in x of n plus 1, we have to give it to the general format as x of n minus of minus 1. So x of n plus 1 can be written as x of n minus of minus 1. So the k value is minus 1, which is negative here. So after obtaining your k value, the starting time period of your x of n should be added. The starting time period of your x of n is 0. So 0 minus 1 is minus 1. So it is shifted from minus 1. It is advanced. So from minus 1, 5 values. So minus 1 to 3. So with this concept, let us do a problem here. So if dt input signal is x of n is 1, 3, 2, 1, minus 2, 3. So here the time range starts from minus 2 to plus 3. So minus 2, minus 1, 0, 1, 2, 3. So total is 6 values here. First, plot x of n in a graphical representation. So this is your graphical representation of the given sequence x of n equal to 1, 3, 2, 1, 2, 3. So time period is from minus 2 to plus 3 and its corresponding amplitudes are marked. Now let's obtain x of n minus 2 and x of n plus 3. In x of n minus 2, the k value is 2, that is positive. So the k value 2 is added to the starting time period of x of n. So the starting time period of x of n is minus 2. So minus 2 plus 2 will be 0. So from 0, 6 values you have to take, that is 0 to 5. So this is the x of n minus 2 signal. So it has been shifted right for 2 values. Next, in x of n plus 3, it can be given into an original form as x of n minus 3. So your k value is minus 3. So minus 3 should be added to the starting time period of x of n. So minus 3 minus 2 will be comes minus 5. So minus from minus 5 6 values. So minus 5 to 0 is the time period, time range of x of n plus 3. Next is time reversal. So the time reversal of a discrete time signal x of n can be obtained by folding the sequence x of n about the origin or about n equal to 0. That is, if x of n is 1, 2, 2, 1, 3 with a time period of 0 to 4 units of time, then its corresponding time reversal will be, so with the origin, above the origin the signal is folded. So after folding the signals, so the time range has been changed from 0 to 4 to minus 4 to 0. So this is time reversal, x of n, time reversal of x of n, which is nothing but x of minus n. So in this time reversal, the shifting can be performed here. So the shifting is whatever the k value they have given, so we have to take it with your sign magnitude here, and then it should be added to the starting time period of x of minus n. For example, in x of minus n plus 1, the k value will be plus 1. So this plus 1 k value will be added to the starting time period of x of minus n. So the x of minus n time period will be from minus 4 to 0. So minus 4 to this minus 4, the 1 will be added. So minus 4 plus 1 becomes minus 3. So from minus 3, the signal has been shifted. So from minus 3 to 5 signals here. So from minus 3 to 1. So your x of minus n is shifted here. So x of minus n minus 1. So in this one, the k value is minus 1. So minus 4 minus 1 will be minus 5. So from minus 5, 5 values. So minus 5 to 1. So this is your time reversing as well as time shifting. So in time reversal, the time shifting has to be performed. Whatever the k value given in the statement, you have to take your k value as such, including your sign, and that should be added to the starting value of your x of minus n, since the x of minus n is going to be shifted. So you can do a problem here. If the signal, input signal x of n is 1, 3, 2, 1, 2, 3. So first step is to get the graphical representation, and then the next step is to obtain your x of minus n. So in your x of n, the time ranges from minus 2 to 3. So in your x of n, you have to fold your signals about the origin. So the 0 to 3 becomes minus 3 to 0, and minus 2 to 0 becomes 0 to 3, 2. So totally the time period will be from minus 3 to plus 2. Now in this time reverse, obtain your x of minus n plus 1. So in x of minus n plus 1, your k value is plus 1. So the time period of x of minus n, starting time period of x of minus n is minus 3. So minus 3 plus 1 becomes minus 2. From minus to 5 values, so 6 values. So minus 2 to 3 is your signal. Next, x of minus n minus 1. So you just try the same thing for your x of minus n minus 1. What's your k value? It is minus 1. So minus 1 should be added to the starting time period of x of minus n, which is nothing but minus 3. So minus 3 minus 1 becomes minus 4. So minus 4, from minus 4, 6 values you have to take. So minus 4 to 1. Next is time scaling. So the time scaling of a signal can be obtained by replacing n by an. in the signal x of n. That is, the time period is scaled by a constant value a. So y of n equal to x of a n. So if x of n is given from minus 3 to plus 3, then its corresponding x of 2n, it is decimated as this. So substitute your n values and then substitute your n value as 0. So y of 0 is equal to x of 0. So x of 0, the value is 4. Y of 1 is x of 2 into 1 is x of 2. So y of 1 is nothing but x of 2. So x of 2 value is 2. So that is obtained as y of 1 here. Then y of 2 is x of 4. So here x of 4 value is 0. So 0 is obtained as the value of y of 2. So similarly, y of minus 1, y of minus 2. Amplitude scaling. So in amplitude scaling, the discrete signals can be represented as y of n equal to a into x of n. Here the amplitudes are scaled by a constant factor a. So for example, if x of n is 1, 2, 2, 1, 3 with a time period of 0 to 4, then x of 3 into x of n is obtained as 3, 6, 6, 3, 9. So the time period will not be changed, only the amplitude is scaled by the factor 3. Signal addition. Signal addition adds the corresponding values of two signals and form another signal. For example, if x1 of n and x2 of n be the two signals, so y of n be the third signal, which is obtained by adding the corresponding values of x1 of n and x2 of n. If x1 of n equal to 1, 2, 2, 1 and x2 of n equal to 1, minus 1, 1, minus 1. So both the time ranges are from 0 to 3. Then your y of n is obtained as x1 of n plus x2 of n, which is nothing but 1 plus 1 will give you 2, 2 minus 1 is 1, 2 plus 1 is 3 and 1 minus 1 is 0. The corresponding values are added. Signal multiplier. Signal multiplier multiplies the corresponding values of two signals and form another signal. So if x1 of n and x2 of n be the two signals, it is multiplied to give corresponding values are multiplied to get us another signal y of n. For example, if x1 of n is 1, 2, 2, 1 and x2 of n is 1, minus 1, 1, minus 1, then y of n is given as x1 of n into x2 of n. So its corresponding values are multiplied. 1 into 1 is 1, 2 into minus 1 is minus 2, 2 into 1 is 2 and 1 into minus 1 is minus 1. Thank you.